Hello viewers, welcome to Timas TV. Today we are looking at electromechanical energy conversion. It is a process where electrical energy is being converted to mechanical energy and vice versa. So that means that um, we can convert from electrical to mechanical and also from mechanical to electrical. This principle is on the principle of conservation of energy. That states that energy can neither be created nor destroyed, but it can change from one form to another. So in this case, you are looking at two types of energy converting between each other. So we can actually demonstrate this principle further by using like a block diagram of electromechanical system. So we can start by writing this electromechanical system. And in this system, it comprises of three systems. We look at magnetic system, magnetic systems. We also look at electrical system. So we have mechanical system. We have mechanical system. So what we get from this system is magnetic field, yes, and we actually have we have speed, we have position, and also have acceleration, acceleration, acceleration. So in the electrical energy, what we have is we have the current and we also have the voltage. So we can achieve this through the circuit equation using Kirchhoff voltage law and Kirchhoff current law. And also achieve this by using force torque equation where we are using Newton's law. We should also know that this can actually be converted to this between each other. So at this point, having explained the systems, we have that three major systems is involved in this process: electrical systems, magnetic systems, and mechanical systems. So on that note, we realize that we can actually present this as if we are looking at generating system, we, we can have mechanical input. This will give us electrical output, and we look at energy in the coupling field, and we also acknowledge losses during the process. So if this is a generating system, so we also look at the motoring systems where the mechanical energy is the output. So this will give us electrical input, electrical energy input. This is equals to mechanical energy output plus energy in the coupling field. We also acknowledge losses during the process of the system output. So in this case, we also realize that having considered this, that we are actually having a stuff like this, electrical system. We have what we call coupling system, and we also have mechanical system. So on this coupling system is like in between the two systems, electrical system, mechanical system during the process of energy conversion. So we have two types of coupling field. We have electrical coupling. We also have magnetic coupling field. So this deal with some systems that convert large amount of energy, like we have generator, we have motors, and etc. Whereas this can actually support a device like microphones. We have big ups, and we also have loud speakers and etc. So we have to acknowledge that the input energy will transfer um, the energy from this state. It's not going to the output directly, but it will pass through a coupling system. It's a coupling system that will release this to this energy. So we should actually acknowledge this. So in doing this, we want to summarize some of the parameters that is very much needed in the magnetic circuit. So in magnetic circuit, we we look at this. This is the flux that comes from the magnetic field and is measured in Webers. We have to acknowledge this. So flux is um, the same as current in electrical circuit. In electrical circuit. We also acknowledge M and F. We call these magnets to motive force. So this is measured in ampere turns, and this is the same in electrical circuit, the same as electro electromagnetic force, electromagnetic force, electromagnetic force EMF. Of course, this is in volts and also this is in amps. So we also need to take note of what we call being represented as B. This is magnetic density. Magnetic density. So this is always in fire. This is the flux divided by the area, and it's always measured in Weber per meter squared. And also, we also have current density. Current density. So this is amps per meter squared. So we also have what we call S, which is reluctance. So this is this stopped, this restrict the flow of flux in the magnetic circuit. We also have equally, we have resistance in electrical circuits. It also resists the flow of current. Now we have what we call H, magnetic field intensity. So it's always H. And magnetic field intensity is actually related with MMF. So we can have this equation that MMF is equals to the number of turns, the turns in the circuit, multiply with the current flowing in the conductors. So this is also equals to magnetic field intensity divided and multiply with the length. So on this note, we can say that your H is equal to Ni Ni divided by the length of the magnetic path. So these are the few relationship and parameters that we have in the magnetic circuit, and we will be using this to solving some of the problems that we'll be having in the next video. Thank you very much for listening.